All right, today we're going to look at a couple of examples of work, power, and energy. Okay, so this first one, we have a coconut. He falls out of a tree. Try and get everything adjusted here. The tree is 12 meters above the ground where the coconut is, and hits a bystander that is 2 meters tall and hits him on top of the head. If it bounces back up 1.5 meters before falling to the ground, and then if the mass of the coconut is 2 kilograms, calculate the potential energy of the coconut relative to the ground at each of the following locations. So basically you got this coconut sitting up here in the tree. Right, so you get the tree sitting up here. From here up to the coconut is 12 meters. Okay, the coconut is going to fall, right? The coconut is going to fall down. You're going to have some person standing here. The person is 2 meters tall. The coconut is going to then bounce off the person's head, and then he's going to fall back down here. Okay, and so this distance from here to here was 1.5 meters, I believe. Yes, before falling back to the ground. And then we end up with the coconut down here on the ground. So we're looking at the potential energy. So that's the U. We know the equation for potential energy is mgh. And so at the first part it says while it's in the tree. Okay, so do we have mass? They told us the mass, right? It's 2 kilograms. We know, or we can look up in our formula sheet, that the acceleration due to gravity is 9.8 or 9.81. I'm just going to go 9.8 meters per second. And then we're just looking for height. So in this first part, A, the height was equal to 12.0 meters because we're at the very top, we're in the tree. So we just have that U is equal to mgh, which is equal to 2.00 kilograms. That times the 9.8 meters per second times the 12.0 meters. So pretty straightforward. Okay, so clear all this. So we get 2 times 9.8 times 12. So we get 235.2. Look at our units. We're going to have kilograms times meters again over seconds. Kilograms times meters per second becomes a Newton. A Newton times a meter, we should have learned, is a joule. Okay, so this becomes a Newton times a meter, which we know as a joule. So we're going to write 235 joules. Okay, so B, when it hits the bystander on the head. Okay, so we're going to look at our coconut here. Same equation, but now what's my H at this point? Well, the coconut's right here on top of the guy's head, and he's 2 meters high. So it's the same equation, so just U equals 2.00 kilograms. That's the 9.8. Meters per second. And now it's 2 meters. It's tall. So now it's just the equation, 2 times 9.8 times 2. And we get 39.2. And again, we'll end up with joules because the units work out the same. See, so it's pretty simple as we go through here. Now it bounces up after hitting the bystanders. Now we have to look at my height at this point. So what is my height? Well, it's 1.5, but this is our reference ground right here. This is where my height equals 0 down here on the ground. So we always have to measure from here. So it's up to 2 and another 1.5. Okay, so my height is actually 3.5 meters. And now again, it's the same equation. So it's just 2 times the 9.8. And now it's times the 3.5 meters in height that we are once we bounced off the head. So again, 2 times 9.8 times now 3.5. And we get 68.6 joules. Okay, D, what's happening in D? When it lands on the ground. Okay, so now he's sitting on the ground. So what's my height when I'm sitting on the ground? Well, I'm on the ground, so my height down here is 0. That's my reference line. So my height is 0. So I can do the equation 2 times 9.8, doesn't matter. Anything times 0, we're just going to get 0. So in this case, I have 0 joules. And then the last question, E. Say when it rolls into the groundhog hole and falls 2.5 meters to the bottom of the hole. Oh, okay, so apparently we have a hole sitting over here that this guy's going to roll into, right? He's going to roll along here, and he's going to fall down here. We have 2.5 meters, but we're going down, right? If this is my x equals 0, so these are positive y's, right? So positive going this way, so negative's going that way. So it's really a negative 2.5 meters because I fell down into this hole. So my coconut's sitting down here at the bottom. So now my height is equal to negative 2.5 meters. So now my potential energy is equal to the m, the 2.00 kilograms, times the 9.8 meters per second, now times negative 2.5 meters. 2 times 9.8 times negative 2.5, and we get negative 49 joules. Okay, so it just depends on where your reference is at. Always go from your reference, and we started that as my 0. I could have made the very bottom 0, and I wouldn't have any negatives. Everybody would be off. I could have made the 12 meters my 0, and then everybody would have been negative from there, and I'd measured from here. So set up your reference. Like you're in charge of your paper. You get to set where your reference is, and we decided usually the ground, something like that, is the best reference. So we're going to start there. Okay, if the coconut is traveling 14.1 meters per second, okay, so now we're giving it some velocities as we go, so let's continue with our picture here. So when it hit the bystander, okay, so right here, my velocity right there is equal to 14.1 meters per second. So right down here, when it gets to this point, we have that velocity. Then 8.4 meters per second when it hits the ground. So it's going to go over here, and my velocity right as I hit, not after I've hit and kind of stopped and rolling. My velocity right as it hits is 8.4 meters per second. So we want to find now the kinetic energy at those same spots. Okay, so let's look at that. So we know our kinetic energy, so let's look for A. Kinetic energy is 1/2 mv squared. Okay, so the V is 14.1 for this case. Oh, well, it's in the tree. Sorry, we're not here yet. We're in the tree. What is the velocity when we're in the tree? We're in the tree and we're just sitting there, right? It's hanging in the tree. Is it moving at all? No. Right, so the velocity right here is 0 because it's just starting. So the velocity in the tree is 0. The velocity is equal to 0. So that makes this equation really easy, right? If that's 0, doesn't matter what these are, anything times 0, we're just going to get 0 and we'll end up in joules again. Okay, look at B. And part B, now when it hits the bystander on the head. So now it's the 14.1. I was just ahead of the game there a minute ago. So now we're going to put that into my equation. So my kinetic energy, my K, is equal to 1/2. My mass is still the 2.00 kilograms. It's still the same coconut. Now my velocity is 14.1 meters per second, and we need to square that. Okay? We do all this. It's going to be 0.5 times 2 times 14.1 squared. And we get 198.8. 198.8 joules. Okay, and then C. What are we doing with C? On C, when it bounces up after hitting the bystander. So we bounced up. Okay, so my coconut is sitting right here now. Okay, so if he's sitting right there, he hit, he bounced up, and then he's going to come back down. So right here, this top of this thing, he's going up, 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 slower, 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 until he basically stops to turn around to go back down. So my velocity again is 0 at that point. Well, we already learned that. If velocity is equal to 0, my kinetic energy is equal to 0 joules. Okay, we like kinetic energy so far. These are easy. And then D, when it lands on the ground. Okay, it should say as it lands on the ground. Okay, not after it's already hit and stopped, but as it's hitting. Okay, so let's figure that, because the other's just going to be 0, so that's no fun. So let's do this one as it's hitting, even though it might not be really clear. So my velocity is 8.4 meters per second. So again, it's just the same thing over and over, just like potential. So it's 1/2 times the 2.00 kilograms times the 8.4 meters per second quantity squared. Put all that in there, 0.5 times 2 times 8.4 squared. And we get 70.6. Okay, let me grab another piece of paper. We're about done here. Now what are we happening in this last part? It says, what was the total mechanical energy when the coconut was in the tree? So we're looking at total mechanical energy. So when it's at the very top up here, what is the mechanical energy? Okay, and this is the total energy that we're going to have. Well, our equation for that is the potential plus the kinetic. So let's look at A. My potential at A was 235.2 joules, right? 235.2 joules. What was my kinetic at A? If I look down here, my kinetic at A was 0 joules. So 0 joules, so we end up with 235.2 joules. So that's my total mechanical energy at the very top of the tree. Okay, how about when it was at its high point after hitting the bystander? So let's look here. So after hitting the bystander, I'm sitting right here. So we'll look at the mechanical energy. So part B, the mechanical energy total is equal to, again, U plus K. So what was the potential right after it hit the bystander? And that was part C. So it was 68.6 joules. Okay, and then after hitting bystander on this one was C. Again, it was 0 joules because remember it's not moving at the top there. Okay, so that wasn't bad. All right, and then why are these different? Why are these different? What happened? So from up here we had energy, right? We lost potential, but we gained kinetic. Okay, so we gained kinetic there, and then it went up here, and now we have less. What happened between here and here that we now have less energy than we started with? Where did it go? Okay, what happened to it is it hit the guy in the head, right? So something happened. We lost some of that energy into the person. I bet he's got a lump on his head, or his head hurts, or something happened to this guy because a lot of energy went into him. Okay, so energy, let's go ahead and spell, energy left coconut system into the bystander. How much did we lose? Well, we lost whatever that is, 140, 170, whatever it is. Okay, so based on what we've learned, what would be the kinetic energy of the coconut after it's falling 3 meters from the initial position of the tree? So we've gone down here, now the coconut's here. We've dropped 3 meters going down this way. We want to figure out what happens at that point. So what have I learned? I learned that energy cannot be created or destroyed, must stay the same. So the total energy, okay, which we call the mechanical energy at the top, is equal to 235.2 joules. Now nothing's really happened, right? He didn't hit anything, so we shouldn't lose any energy between there and there outside the system. Okay, it's only when we hit the guy's head. So if that was my total mechanical, the total mechanical energy at this 3 meter fall should be 235.2 joules. It should also be equal to my potential energy plus my kinetic energy. Okay, well, why does that matter? We're looking for what would be the kinetic energy, so we want to look for this guy when I've fallen that far. So we can say that the kinetic energy is the 235.2 joules minus the potential energy. So what do we have to find? That potential energy. So what is this potential energy at that, dropped 3 meters? Well, let's look at it. Potential energy is mgh. We know the m was 2, the g was 9.8. What is his height? If I've dropped 3 meters, if I started from 12 and I've dropped 3, 12 minus 3, we should be at 9 meters right there. So my height at that point is 9 meters. So my equation becomes 2.00 kilograms. Okay. My acceleration due to gravity is 9.8 meters per second squared. And then my height now is 9 meters. So I'm going to solve all that. 2 times, not divided by, how about times 9.8 times 9? I get 176.4 joules. So now I want to find the kinetic energy, so I'm going to rewrite this equation. It was 235.2 joules minus the potential that I now have at that point, minus 176.4 joules. Let's see, 235.2 minus that answer I just got, and I get 58.8 joules of kinetic energy. Okay, so now bonus time, super bonus problem. What is the velocity of the coconut? How am I going to solve for that? I know the kinetic energy is 58.8. joules. I also know kinetic energy is 1/2 mv squared. Maybe there. Velocity. So if I solve for velocity, if I multiply both sides by 2, right, I'll go that. We multiply that side by 2. So I have 2 times 58.8. Okay, then I'm going to divide by m. That goes away, so I divide this side by m. And then I have to take the square root. Get rid of that. So I have to take the square root of this. That should be my velocity. Okay, so now we're going to have the square root of 2 times 58.8 divided by the mass, which was 2 kilograms. Take the square root of all that. So we take the square root of 2 times 58.8 divided by 2. Oops, I don't need that. I think I typed all that right. I think it's 7.6, 7.7 meters per second. Okay, there you go. And that's how you solve potential kinetic and mechanical energy problems.